I'm working through the chemical equilibrium section of the 2019 chemistry exam, and the first part of this equilibrium section is question 1.5 in the multiple choice, which reads as follows. Consider the following balanced equation for a system at equilibrium. Equation given here. How will the addition of a catalyst to the equilibrium mixture affect the yield and reaction rate? Now, we know that a catalyst affects the reaction rate by lowering the activation energy, but this affects the reaction rate in both directions, which means that the reaction rate is certainly going to increase, but because it increases the rate in both directions, it does not affect the yield of the reaction at all. And so the correct answer we're looking for is yield remains the same and reaction rate increases. The correct answer there being option C. Question 1.6 is also a chemical equilibrium question, which reads as follows. A hypothetical reaction reaches equilibrium at a certain temperature in a closed container according to the following balanced equation given here. Which one of the following changes to the equilibrium conditions will result in an increase in the equilibrium constant Kc? Now, it's important to remember that our equilibrium constant Kc is equal to the concentration of the products over that of the reactants, but this product over here, carbon, is in solid form, and therefore the concentration is not considered, or the concentration is taken to be 1. So our equilibrium constant Kc is equal to 1 over the concentration of A, which is a gas, multiplied by the concentration of B squared. That squared comes from the coefficient of B. And the question asks, how would we increase the equilibrium constant Kc? The only way to increase this equilibrium constant would be to decrease the concentration of our reactants, to decrease the concentration of the reactants. And we would do that by favoring the forward reaction, because the forward reaction uses up reactants and produces more products. Now, also important to remember that it is only a temperature change that can affect our value of Kc, so that means that options C and D are not options. And then what we use is we use this enthalpy here given delta H less than 0, which tells us that the forward reaction is exothermic, meaning the forward reaction gives off heat. So in order for us to favor the forward reaction, we need to use Le Chatelier's principle, which says that if we decrease the temperature, by decreasing the temperature, the reaction would favor the direction that would attempt to undo that change. In this case, that means favor the exothermic reaction, favor the forward direction. So the correct answer here is option B. Again, that is because we would like to decrease the concentration of the reactants, and we do that by favoring the forward reaction, and we favor the forward reaction by using the Chatelier's principle, which tells us if we cool the reaction down, it will attempt to heat itself up by favoring the exothermic direction. The question 6 in the chemistry exam is always the question on chemical equilibrium, and question 6 reads as follows. Initially 60.8 grams of pure carbon dioxide, CO2, is reacted with carbon solid, in a sealed container with a volume of 3 cubic decimeters. The reaction reaches equilibrium at a temperature T according to the following balanced equation. 6.1. Define the term chemical equilibrium. The definition as given in the exam guidelines is a stage in a chemical reaction when the rate of the forward reaction is equal to the rate of the reverse reaction. Very important that it is the rate of the forward reaction. It is not that the forward reaction equals the reverse reaction. Question 6.2. At equilibrium, it is found that the concentration of carbon dioxide is 0.054 moles per cubic decimeter. Calculate the equilibrium constant Kc for this reaction at temperature T. Now, there are many options for how you can answer this. I prefer to use what is called a Schreck table or an ice table. It is just a simple way to keep track of what we start with, what we end with, and how it changes. And so what I've got here is I've drawn up a Shrek table that shows the starting amount in moles. You'll note that they do not mention the amount of carbon solid, and we are only concerned with the gases when it comes to our equilibrium constant Kc. So the starting amount of CO2 was given as 60.8 grams. Now we need to start by converting that into a number of moles using the formula number of moles is equal to the mass over the molar mass, mass given as 60.8, molar mass of carbon dioxide is 44, which tells us that our starting number of moles is 1.382 moles. And we can put that into our table, 1.382 moles. We are also told it is added into a sealed container, which means that there is no carbon monoxide present at the start of this reaction. We then look at the next bit of information that we are given, which tells us that we end with 0.054 moles per cubic decimeter, a concentration of carbon dioxide. So that is the concentration at equilibrium, 0.054 moles per cubic decimeter. That is the unit there, moles per cubic decimeter. Now, in order to compare the number of moles here, I need to convert this into a number of moles, and we do that by using the formula our number of moles is equal to the concentration multiplied by the volume. Concentration given here, volume given as 3 cubic decimeters, which tells us that our end amount of carbon dioxide is 0.162 moles. What this now allows us to do is it allows us to compare what we started with what we ended with. If we started with 1.382 moles and ended with 0.162 moles, that means we must have used up the difference, that being 1.22 moles. I put a negative here to show that we have used that up in this reaction. Now, as we can see from this balanced equation, the carbon dioxide reacts in a ratio of 1 to 2 with carbon monoxide, which means that if we used up 1.22 moles of carbon dioxide, we will form 2.44 moles of carbon monoxide. And then since we started with nothing and formed 2.44 moles, that means that at equilibrium we must have 2.44 moles of carbon monoxide present. And we can then, once again, using our volume, we can say concentration is number of moles over the volume, 2.44 divided by 3 cubic decimeters. That is then 0.813 moles per cubic decimeter, the concentration present at equilibrium. And finally, to answer the question, the equilibrium constant Kc is calculated as the concentration of the products. In this case, the product is carbon monoxide to the power of its coefficient, divided by the concentration of the reactants. In this case, we only consider carbon dioxide as a reactant because carbon is a solid with an assumed concentration of 1, and we substitute the values that we have in here. That is a concentration for carbon monoxide of 0.813. We square that, divided by the concentration at equilibrium of carbon dioxide, 0.054, which tells us that the equilibrium constant at equilibrium here is 12.24. Question 6.2.2 now reads, calculate the minimum mass of carbon that must be present in the container to obtain this equilibrium. And this is done by realizing that carbon dioxide, which is the one reactant, reacts in a ratio of 1 to 1 with the carbon given from the balanced equation. And since we reacted 1.22 moles of carbon dioxide, that means that a minimum of 1.22 moles of carbon must have been present. Now the question asks what mass was required, and we once again use the formula. Our number of moles is equal to the mass over the molar mass, number of moles that we have calculated 1.22 over the mass, that is our unknown, and the molar mass of 12 grams per mole, which tells us then finally that the mass required was 14.64 grams. Important to note that this is a requirement for how we substitute into a formula. You always write down the formula as it is given. You then substitute the values that you have and then rearrange to find the answer. Obviously important to have the correct units present there. Question 6.3 now reads, how will each of the following changes affect the amount of carbon monoxide at equilibrium? Choose from increases, decreases, or remains the same. Question 6.3.1, more carbon is added to the container. Now, it's important to see here that the carbon, once again, is in solid form. And since this carbon is in solid form, it does not have a concentration that affects the reaction in any way. And as a result, as long as there is enough carbon, which we have shown in the previous question, as long as there is enough carbon, the amount of carbon present in this container has no effect on the amount or on the equilibrium. And so the correct answer here is that it remains the same. Once again, that is because carbon is in solid form. Solid form has a fixed concentration, and by increasing the amount of carbon, we are not increasing the concentration present. Question 6.3.2 says, the pressure is increased by reducing the volume of the container at constant temperature, and use Le Chatelier's principle to explain the answer. In order to answer this, we need to realize that the reactant side of this reaction, once again ignoring the solids, has only one molecule or 1 mole of gas present. There is only the 1 mole of carbon dioxide, where the forward reaction or the products here produce 2 moles of substance, because there are 2 molecules or 2 moles of carbon monoxide present or formed from every 1 mole of carbon dioxide. And so in answer to the question here, when the pressure is increased or when the volume is decreased, Le Chatelier's principle is going to favor the direction that reverses that change. So since there is now less volume available, that means that the reaction is going to favor the direction that produces fewer moles of substance, which in this case is the reverse reaction. So the reaction is going to favor the direction that produces fewer moles of substance, and when it produces fewer moles of substance, it uses up product to make reactants, and what that then tells us is that the amount of carbon monoxide, our product, is going to decrease at equilibrium. And the explanation there is that when pressure increases, the reaction favors the reverse, favors the direction that produces fewer moles of substance. Reaction favors fewer moles. And as we have shown here, that means it favors the reverse reaction. And because it favors the reverse reaction, it is going to use up the product, the carbon monoxide, and produce more carbon dioxide. So once again, we say that the amount of carbon monoxide decreases when pressure is increased. The reaction that leads to the smaller amount or number of moles or volume of gas is favored, and that means that the reverse reaction is favored in this case. Question 6.4. The table below shows the percentages of carbon dioxide and carbon monoxide in the container at different temperatures. 6.4.1, is the reaction exothermic or endothermic? Refer to the data in the table and answer the question. Now, by looking at the table, we can see that as the temperature increases, we can see the temperature increases down the table, the percentage of carbon monoxide increases as well, from 93.77 to 99.94. And at the same time as the temperature increases, the amount of carbon dioxide decreases. What this would suggest to us is an increase in temperature you can write here, an increase in temperature leads to an increase in our products, which means that the forward direction is favored. Now, since we are favoring the forward direction with an increase in temperature, Le Chatelier's principle would suggest to us that the reaction must then be endothermic. It must be endothermic because the forward reaction being endothermic would mean that as the temperature increases, the forward reaction is favored because it produces more of the products. So we are favoring the forward reaction with an increase in temperature, which means that our forward reaction must be endothermic, and the explanation is just that. We say an increase in temperature increases the number of moles or increases the amount of product. We could also just state here that it increases the amount of carbon dioxide, which suggests to us that therefore the forward reaction is favored with an increase in temperature, which tells us then that it must be the endothermic direction. So we say therefore the forward is endothermic by Le Chatelier's principle. So once again, we say that this reaction is endothermic because when the temperature increases, the percentage carbon monoxide or reaction or forward reaction is favored, and therefore an increase in temperature favors the endothermic reaction. That is question 6.4.1. Question 6.4.2. Use the information in the table to determine temperature T. Clearly show how you arrived at your answer. Now we can do this by referring back to our original Schreck table, because that can tell us what the total volume occupied in this container was, because we can say that the total volume occupied in this container at equilibrium is the sum of the volume occupied or number of moles occupied by carbon dioxide as well as carbon monoxide. So we can say that the total must be the sum of those two, that being 0.162 combined with 2.44, which tells us that the total is 2.606. So this tells us that at equilibrium, the total number of moles of gas is made up of the number of moles of carbon dioxide, 0.162, plus the number of moles of carbon monoxide, 2.44, which says that the number of moles is then 2.606. What that allows us to do is then it allows us to calculate the percentage CO2 at equilibrium by saying at equilibrium there was 0.162 moles of carbon dioxide out of the total 2.606 moles, and to convert that into a percentage we multiply by 100, and that then tells us that there were 6.225% carbon dioxide at equilibrium. We can now look at our table to see that this number matches with the temperature of 827 degrees, because at 827 degrees there was 6.23, which is obviously just the rounded number here, percent of carbon dioxide, which tells us that the temperature at equilibrium must be 827 degrees Celsius. Just to go through that once again, we have used the original calculation that we did, our Schreck table, to show that we know at equilibrium there are 0.162 moles of carbon dioxide and 2.44 moles of carbon monoxide, which allows us then to calculate the total number of moles of gas present at equilibrium, 2.606 moles. And once we have that, we can then calculate the percentage carbon dioxide. We could also use this to calculate the percentage carbon monoxide, and we would find this value. And then we can, by comparing this to the values in the table, see that this is most similar to the temperature of 827 degrees. And so our final answer is to say that the temperature T is 827 degrees Celsius.